stream from my phone, so I can only imagine how terrible that was. So this should be a whole lot better. 263, yeah, right, because we did A and B, we just haven't done C yet. Is that where we're at? With the whole ladder leaning up against the wall, like this.
Yeah.
Sweet. Howdy.
Howdy.
Take any of these kind of open seats in this general area. What's up, Noah? She should be back shortly. She's going to come pick you guys up, but she's just on her way back from the house. So you guys should have whatever stuff you need to get done. So go ahead and get started on. Okay. You can watch us do calculus if you want. All right. So wasn't the base of the ladder 7 feet away for A and B?
Oh, yeah.
Now what is it? So like a whole second has passed, right? Because wasn't DVDT 2?
Yeah.
So we're looking kind of like a second into the future. But the thing that I think is important for us to remember is that this is the only constant in this problem, right? That length, 25, is the only thing that's going to stay true. And even though we know what B is, even though we can figure out what H is at that moment, I think it's important to remember that when we're doing these related rates, that we keep in mind the things that are changing over time, and that we don't drop those constants in too early. Like I don't want to say, hey, B is 9 right now, and H is whatever, right? Pythagorean theorem will figure it out. And then we differentiate now, right? We want to differentiate before we plug anything in. And so some of the advice that I may have neglected to mention in the past, for me, when I do related rates, is I actually draw the picture out twice. Now, you don't have to, as long as you can kind of keep track of some things. But for me, what I do is I draw the picture of things in motion, and I leave them as variables, and then I write in the things that are true about that moment in time. Right? You don't have to, but it's important to realize that if we're doing related rates, we have to have at least 2 of them in there, so we need 2 variables to go with it. Now, we've been doing dB/dt, dH/dt. Find the rate at which the angle being formed by the ladder and the wall, so that right there. Let's figure out how fast that's changing. Now, this is still part C of a much longer problem. So we know dB/dt, we know dH/dt, so we can use those. We might need all of them, might need some of them. As this ladder gets kicked out, is that angle going to change? So we don't want to put in just a number for it. We need a variable to represent that unknown angle. What do you think we should do? Theta sounds good. Okay, so that's theta right there. And we'll figure out whatever we can, if we want to. We can figure out whatever that theta is. But let's design, because here's the snapshot, right? Let's design an equation that will relate that theta to the triangle that it's in. And these are the things that we know right away. Of course, we can solve for H. We might need to. Let's see how it plays out. But those are the things that we know for sure. We know the opposite side, and we know the hypotenuse of this right triangle. What should we use to relate theta to an opposite side and the hypotenuse? So, right? But the thing that I'm not going to do is I'm not going to say sine of theta equals 9 over 25, because we want that base to still change as we go. And so when I design my initial equation, I always use the first picture, right? The thing that's moving, the thing that's changing as we go. And then eventually I'll drop in the 9 for B. And I don't know if I'll even need H, so I'll just leave it kind of off on the side. If we eventually need it, we'll just solve for it. But now we have ourselves an equation. I know in the past it's been volume and area and surface area and whatever. Okay, cool, let's just do trig. This will probably be the last time I do this where I write ddt both sides. Okay, you don't have to do this. I just kind of like to keep myself going a little slower, especially early on. And I'm going to pull out the constant, call it 1/25 times b. So that when I differentiate, I can just pull out the 1/25 and then just differentiate. Does that setup make sense? We cool with how that works out? And this is kind of the only one that is unique. Once we turn the page in 264 and beyond, you're going to see we've got all the skills now. It's just spheres, cones, triangles, basically, for the most part. Maybe some cylinders, things like that. So all right, let's differentiate sine. What's the derivative of sine? Cosine. Now, okay, so cosine theta, but the variables don't match because it's theta and t. So we need that differential attached to it. And it used to be like dB dt or dH dt or dV dt. What is it now? d theta dt. And that's what we want, right? Find the rate at which the angle is changing. That's going to be our d theta dt. So that's what we want to solve for. So we'll definitely have to figure out cosine. All right, let's differentiate the right side first. So pull the constant out, 1/25 times the derivative of b with respect to time. Okay, dB dt. Sounds good. If that was like b squared for whatever reason, okay, 2b dB dt, right? If that was b cubed, okay, 3b squared dB dt. This is just linear, so we're good to go. So solving for d theta dt, we have dB. Do we know dB dt?
Yeah.
That's still 2. Same problem, right? Okay, so ABC, so we can still use that. We just need cosine. We just got to figure out the cosine of this angle in the moment, right there, right then. So adjacent over hypotenuse. So we need that. If we can figure out that, we'll do that over 25, and that'll be our cosine. How are we going to figure out that length? Pythagorean theorem. Okay, so sneak it in somewhere. I should have left myself a little more space because I knew this was going to happen. I don't know, call it h squared. H squared plus 9 squared equals 25 squared. So let's see. 81 from 625. 544, I think. Anybody back me up there, calculator? Yeah, 625. Yeah, that works. Oh, but square root though, right? Oh, geez. Is that perfect? Yeah, I don't know. Is this a Pythagorean triple? Is this 3, 4, 5, or any multiple of that? Is this 5, 12, 13? 7, 24, 25. Well, it was so nice when it was, right, for part A and B. Now we're a second later. 8, 15, 7, no, right? So that means this isn't going to be perfect. But is there a perfect square factor of 544 to at least make it simpler? Is there a number that goes evenly into 544? 4, okay. But what's left after that? Like, is there something bigger? Does 9 go in? Because if 4 goes in, maybe 16 goes in. Right? If 4 goes in, maybe 100 goes in. Right? Product of 2 would work. What's up? You from Mrs. Rosengrant? Just grab a seat. She'll be here in a second. Is there a perfect square factor of 544 bigger than 4? Because I think you're right. I think 4 goes in. 16 go in. What's left after that?
34.
16 and 34? And 34 doesn't have any perfect square factors, so let's call it 4 root 34. Nice. Now, I think, and I'll check this to be sure, but just like we don't have to rationalize denominators, you don't have to simplify radicals in FRQs. But if this was a multiple choice, I bet they would have done that. So you want to make sure that we've got that. So cosine of theta is, so 4 root 34 over 25, there it is, adjacent over hypotenuse. Here's what we want, d theta dt. And then this times, was it 2, right? And positive 2, right? Because we're kicking the ladder out. So the base is increasing. Okay. So how are we going to solve for d theta dt?
Multiplied by 25 over 2.
Yeah, don't create complex fractions by dividing by the fractions multiplied by the reciprocal. So let's take this fraction right here, which is just 2 over 25, and multiply it by the reciprocal, 25 over 4 root 34. I'm just going to go to the right because I'm out of space there. Anything we can simplify? Anything that kind of makes life a little bit easier to look at?
25.
25s for sure. Anything else?
4.
Yeah, and that was the benefit to actually going through all that process to simplify, because now we just get 1 over 2 root 34, which isn't bad. And again, no need to rationalize. You don't have to multiply by root 34 top and bottom. You can if you want to. But calculus don't have to, so that's good. Now, it's been like feet per second or square feet per second or cubic meters per second or whatever, per minute. This is d theta dt. What angle measurement system do you think we're probably going to use in Calc? Radians versus degrees is kind of the question, right? What do you think? Upper level stuff, which one do you think we're better at? Radians, always radians. Good. Radians per, is it minutes, hours, seconds? Seconds, cool. Radians per second. Which is about, and this is a very rough estimate, it's about 5 degrees per second. And I wanted to know that, because that is obviously a really small number. 1 over 2 over 34 is like 0.008 radians, it's pretty tiny. I just wanted to know what that was in seconds so I could feel like I had a decent answer. I didn't get 100 degrees per second, right? Just didn't go smack, right down to the ground. But it also wasn't 0.0006 degrees per second creeping its way slowly down the wall. This base is getting kicked out at 2 feet per second. 5 degrees kind of feels about right? Having that common sense setup, the kind of answer that we're hoping for, works out pretty well. I went the much harder route first time around. I actually solved for theta initially in the blue one, and I had theta equals arc sine of b over 25. And the derivative of inverse functions is something we haven't done, and it actually made it a whole bunch harder. In case you wanted to see what it is, ddx of arc sine of x, I'm not even going to do ddt, I'll just make the variables the same. It's 1 over the square root of 1 minus x squared. And so let's make the variables not match by doing d dt of arc sine of theta, and we need a d theta dt after that, right? Or d theta dt on top. That'd be fine. And that just caused a whole big disaster for me when I was trying to solve it. I was like, well, why do all that? Here's a nice equation, sine of theta. Let's take our d dt of both sides. Worked out real well. Obviously, there seemed to be some side work we needed to do to get there, but at least that kind of covers it. That kind of like gets us all the possibilities. Proportions with similar triangles for sure comes in, especially with cones, right? We see that a lot. Volume, surface area, area of spheres, cones, cylinders, circles. Basically, we've got it. We've seen them all so far. And what the next 1, 2, 3, 4, 5, 6, 7 pages do for you is give you a chance to try it. Now, before you get started though, so page 263 now done, page 264, love all 3 of those, you like them. Go to 265 real quick, just flip for a second. Okay, this is not a page of specific scenarios where they ask you to do related rates. This is whether or not you can do implicit, just period, okay, with those kind of equations. So look at number 1, right? Here's an area of a circle. Write an equation that relates dA dt to dr dt. That just means implicitly differentiate both sides. Okay. Same thing with 2. Here's a surface area. See how I use S for surface area, not A? It's a good idea. Okay, it's just unique that way. And so even though I might have used A on the page book, yeah, I used A on the page before, it's all good. Either one's fine. So I don't think you need to bother with 1 and 2, personally. If you want to, great, go for it. But I think you can skip it. 3, 4, and 5, potentially skippable, but I think a worthwhile exercise for you because of the fact that they are asking us to do 3 different things with the same volume equation. Number 3, really, right? Number 3, what if H is constant? Right, how do I differentiate? Treat H like a constant and avoid having the dH dt in the problem. Can I do that to make my life a little bit easier? Worthwhile to check out if you want. Same thing with 4 with R, right? Treat R like a constant. So pull that R squared out and so you don't have to deal with it. That's cool. And then 5, what if they're both variables? Right? Now you have 2 different variables being multiplied. Can you do the product rule with implicit? So I like 3, 4, and 5. So if you look at my paper right now, you will see that I left 1 and 2 blank, but I did 3, 4, and 5 as part of my solutions. Okay? That's up to you. Totally up to you how much or how little of page 265 you want to do. But the other 6 pages are awesome. Okay? And I've got the answers to the first 5 already. I'm going to sit, well, I'll do a couple, I guess. But I want to get these solutions done today and out to you via Canvas. Because if we can, I would like today, this last half hour or so, to kind of be the end temporarily of related rates. Coming back to it Monday / maybe Tuesday as we review for Friday, right? Our finals on Friday of next week, so we have a little bit of time, so that's good. But I want to get to the second derivative stuff. I want to get to the second half of chapter 2 or chapter 4, and at least then we can decide what do we want to do Monday and Tuesday. What am I still struggling with? What do I got? And you can kind of work on your own maybe, or work together and like let's do a related rates, little like mini lesson over here, and you guys can do second derivative stuff. Does that sound good? So here is what I think we should do with our last half hour. So turn to 264. Let's at least maybe do one more together, just so we can kind of get the flow going of a brand new problem. And then you can have at it, right? Because now you see, finally, they've gotten to the point where they just say, okay, here's some empty space, right? Do what you need to do to set up your, and for me, 2 pictures, one in motion and one pretty static, and then get after, okay? So let's do it. They like this question a lot for sure. This airplane flying over some stuff, okay? Airplane flying at an altitude of 5 miles, passes directly over a radar antenna. That's kind of the, like, if I stop time right there, that's what I see. An antenna down here, and you don't have to label the vertices, I might as well go. Antenna down there, and then the plane up top. Here is the plane at the beginning of time. I'm going to call it P sub 0. Plane doesn't stop though, right? It keeps going. And at some point, when I stop again, here's the plane over there, right? I'm going to call that P sub 1. Now, I don't know how many seconds that is later. I'm going to put P sub t. Whatever. You don't have to label these at all, but just so we know what we're talking about, okay? So this is kind of my setup right here. Now, this distance right here is going to change depending on where I decide to stop, right? And so although they say, hey, when the plane is 10 miles past, right? So I've got 5 and 10 eventually. I don't want to, in my setup where I have 2 different versions, I don't really want to put 10 here because this is going to be changing. When the plane is 10 miles past the antenna, the rate at which the distance between the antenna and the plane is changing 240 miles per hour. What is the speed of the plane? So we don't know this and we don't know that. Okay, I don't know, A for airplane, D for distance, call it whatever you want, doesn't matter. X and Y, A and B, A and C, E and Q, you get whatever letter you want. Okay. So we know how fast this is changing. We know dd dt. If that bothers you that it's dd, then just pick a different letter. Okay. We know dt is 240. We want to know the speed of the plane. What rate is that, do you think? Given my picture up here, which rate of change are we looking for? The speed of the plane moving straight across. dA. dt is what we're hoping to find. Okay? And so what we need is some equation that relates the sides, because they don't talk about angles here, so I don't need sine or cosine. What do you think? What shape did we just draw? Okay, so what formula relates all 3 sides of a right triangle? You don't have to put 5 squared, you can call it 25. And I guess we'll probably need D. Well, I will probably need that, but I'm going to leave it blank for just a second until I see if I need it or not. But let's differentiate both sides with respect to time. If you need to write the step, ddt of the left, ddt of the right, go for it. If you're good enough to say, okay, I'm ready to do it, let's do it. 2a dA dt for a squared plus, what's the derivative of 25? 0. Okay, so leaving that blank equals, so I don't even need the plus 0. And then 2d dt dt. Again, if the dd bothers you, then call it B or C or whatever. Okay. Good to there so far? Do you think you could have set it up like this on your own just yet? Some of us, yes, some of us, no. And so I think that this is worthwhile time. Okay. All right, let's do it. 2 times. Okay, now instantaneous rates of change and static distances at this moment in time. So A is 10. dAdt, oh, that's the speed of the plane. That's what we want. We want to figure that out. So dAdt, leave that as dAdt. 2 times, yep, there it is. We got to figure out d. So trying to figure out this distance. So still the right triangle. So Pythag 25 and 100 is 125. We want the square root of that. So square root of 125, so 5 root 5. Cool, that'll be right here. 5 root 5 times weighted rates, got to have 2 of them. Asking for 1, they better give us the other 240. Now, is that positive or a negative? Is this distance increasing or decreasing as this plane continues to go in? Positive it is, 240. And we're in miles per hour, so that'll be the speed of the plane. We'll be in miles per hour. And now we just simplify and solve. 20 dAdt. And then, 10 to 240 root 5, or 2400, sorry, 2400 root 5. So dAdt, 5 both sides by 20, so 120 root 5. Miles per hour. The distance, so it's not square miles or cubic or anything like that. You can put miles per hour, you can put mph. If you wanted to abbreviate miles, it's mi. Why don't we use m, do you think? Meters. Yeah, question.
How did you get the 5 root 5?
Pythagorean theorem. I didn't write it down, sorry.
Oh,
I did that.
okay.
25 and 100 is 125.
Uh-huh.
So d is the square root of 125. Just like the 544, we could simplify. I broke this apart into square root of 25 and square root of 5.
Okay, thank you.
Mm-hmm. So good side work to show in case you need it. It wasn't a special right triangle, so couldn't use that. That's good. And it wasn't Pythagorean triple either, right? I wish it was. 3, 4, 5, 5, 12, 13. Those, they like that as often as they can get them in, but they'll mix these in. Okay. Personally, I probably wouldn't write miles per hour like that. How do you think most of us are going to write miles per hour? Yeah, right? We're used to that. That's cool. That's fine. I did. That should just about do it. Everything from here, I mean, you'll see that we'll get into some like area of rectangles, perimeter of rectangles. So we'll have some area formulas that we just haven't used yet, but we know what those are. Diagonals of a rectangle, a lot of Pythagorean theorem, volume, surface area. Definitely some similar triangles within the cone when they talk about the height and the radius, like we've seen a couple times now. That comes back again for sure. So anything, of course, we'll finish 264 right here. Maybe I'll do those two, but I'll let you work. I'll let you try them out and make sure you can get them on your own. 264, I'm just going to skip 265 completely today, okay? But I'll put them up on Canvas. I just wanted to finish. I'm at the bottom of 269 right now with my answers, so I still have 270 to go. But yeah, 20, 25 minutes to just try some out. I'm going to try to stop talking, but you know me, and just kind of see what comes up and let you work and give you a chance to try these out. So I'm going to do 264 and then 266. It's probably about as far as we get today. Nothing you need to hand in to me, nothing on Canvas necessarily. But my suggestion is by next something, Wednesday, Thursday, Friday of next week before the final, you probably want to get the rest of this under your belt. You want to kind of have these done at some point. And I think we'll have time Monday and or Tuesday kind of dedicated to review, because if we can do second derivative stuff Wednesday, Thursday, Friday, I'm hoping that's enough. Maybe not. We might need Monday. So we might only have one day of review. But thinking ahead to the final, it'll be just basic implicit stuff with x's and y's, right? Equations that just aren't explicitly a function of x. Related rates as an application of that. And then some second derivative stuff. And that's going to be it. So I'm going to stop talking quite so much and work through the bottom of 264. Talk it out. Do your own thing, whatever works for you. And then ask questions as things come up. One last thing I'm going to say, here's how I draw a sphere. Circle, arc in front, yeah. And then dotted arc in the back with a radius. Yeah, sure. Oh, not equals. Sorry.
What any of the information is that?
96 pi. Surface area, so square inches or inches squared per minute. Doesn't get any easier than that one, probably. Ooh, the next one's a good one. Nice. We get 96 pi. Anybody need to see that one, second one? So there's the second one. One last time. There's middle of page 264. We want a surface area rate. So S equals. Now A equals is fine. If you put A equals, that's cool. I think I even did on the answers. But there's the middle of 264. The bottom of 264 is a little bit more challenging because they're giving us a volume rate and asking us for a surface area rate. Those are not in the same equation. But they do have a rate that they share from one equation to the other, the radius. If we can find dr dt, we can use it. And since we know this, right, 4/3 pi r cubed, we can differentiate that, solve for dr dt, and use that in our ds dt. Ooh, that's a good one. I like that. 4 pi r squared dr dt. 60 pi 4 pi 4 squared dr dt. 64 pi dt is 15 over 16? Positive, right? Expanding. Sorry. Don't look until you're ready. I'll stop talking. Nice. Again, skip 265 for now. I like 3, 4, and 5 just to make sure your implicit stuff is feeling pretty good. You can tell what to do when things are constant and when they're not. When do you have to use the product rule and when don't you? Square inches or inches squared, either one's fine by me. This is probably the most common, actually, just for conformity, just so that everything looks the same, whether it's imperial or metric. So I'm doing either.
Oh, yeah, probably 5, 5.
Another minute or two for this one, and then I'll go to 266. 267 is pretty easy.
Okay. I'm just skipping one.
Usually anything with the cone uses a similar triangle so that we can get it down to one variable instead of two. Isolate R so we can just do things in terms of H. Or vice versa. Depends on what rate they give us. Or they're asking for. All right, so 11 on 267, find the rate of change for the depth, so the height of the water. So I need DHT, so it's got to be in terms of H, so I can get a DHT. But that's getting ahead of myself. Uh-huh. I'm gonna turn. Again, skipping 265, going to 266. I'm drawing two pictures. One that's gonna move and one that's gonna stay. Length and width, 12 and 12. He's quietly judging you from a distance. Always does.
He's every mistake I make like that.
You see him shaking his head at you. DW is increasing. DL is decreasing. (24 minus 14 centimeters squared per second).
Oh, yeah, no.
Mr. Rosegren says the length is decreasing.
The length is decreasing, correct. That's why my dl dt is negative 2. Yeah, because L and W are still measurements, so they have to be positive because we're measuring distance. It's the rates that we're going to pick, positive versus.
Well, I did one here, but I didn't.
I think we did that one.
Oh, this is what we're doing.
I got 2 pi r h d r dt plus pi r squared dt. You do it seconds.
Oh, yeah, but it's a plus, I don't know how you.
For this area, can you
I'd rather-
Say again?
For like surface area versus area, this area would be
So you
A.
had.
Yeah. So area of a 2-dimensional object, I put A. Surface area of a 3-dimensional object, so a 2-dimensional measurement of something 3 dimensions, I usually put S.
Oh, so it's 2HR. Thank you.
Yeah.
Oh, yeah, we forgot about that one. I literally want to leave it in this one.
L is usually written cursive for length, so it doesn't look like a 1. So there's my cursive L, kind of like T, right? Put a little tail on it. I make it look like something else. The length decreases and the width increases. Our area is getting bigger. Do you know what rectangle for a given perimeter has the largest area? So if I give you a certain amount of fencing and you want to create the largest area, do you know what rectangle will give you the biggest area if you limit the perimeter? The regular version, the square. And that's true for every shape. If I force you to have a certain amount of material, like so this much fencing, and I say turn it into the largest area for a 5-sided shape that you can, it's a regular pentagon. It's always the regular version, which means regular just means same angles everywhere and same side lengths. Yep. So equilateral triangles, we're going to maximize area. Squares are going to maximize rectangles, which is why when they say like the length is decreasing and the width is increasing, that's why the area is getting bigger. Because you go from a rectangle that looks like this, and we're like stretching it this way, squishing it that way, trying to get to that square. And take a look. What degree is the area equation? What degree? What degree is this? Length times width? Second degree. What kind of equation is degree 2? Quadratic, right? And so there's going to be a maximum.
Yes.
Right? It's going to have a maximum.
Oh.
It all works. It's amazing, right? The length is decreasing at the same rate the width is increasing. That's why the perimeter is not changing. Yeah.
How come for the area one, it's LD, oh, product rule, never mind. I got it now. I thought it was
I know. Wouldn't that be nice if it was just like DLDT, DWDT? We wouldn't have to worry about it. Yeah, that would be nice. Dang you, Einstein. I guess I should say Newton, right?
Yeah.
I'll blame Newton for it. Well, Leibniz gets the love too. All right, I'm going to do 8. Are we good? Take pictures if you want, but again, the answers will be up by this afternoon, so you won't have to. At least I hope so. That's the plan. Here we go. Same picture, but I want that right there. Length, width, diagonal. So really, the only picture I care about is that one. So there's a picture of things changing. Here's the picture of it being stuck. 5, 12, 13. Thank you. Thanks, Pythagoras. Love you. All right, L squared plus D for diagonal.
Just double. Oh, yeah, I see. When they get
Did you get 0.7?
Yeah.
Okay. That makes sense.
Right? So perimeter can't change if the length and the width are changing at the same rate in opposite directions. So yeah, 0 centimeters per second for 7. My goodness, let's see. 2 times 15 times, what do we want? Where's my stuff? There it is. We want the diagonal, so we should know dl dt, dw dt. Again, d dt if that bothers you. All right, something else, but it's fine. It's all good. Fast forward to here.
Oh, it's 13.
Negative 14 over 13 inches, centimeters. Yeah.
Why is it 2 times 15?
I don't know. That's a great question. It should probably be 12, right?
Yeah.
There we go.
Oh.
Oh, that's 8.
Thanks.
Oops.
24, 48. Negative 48 plus 1. Yeah.
The diagonal direction of this should triangle. What is the length?
They were really nice with 9 and 10 on the next page to break the question apart, which they didn't do when we did 264 and just asked us for the surface area. So that was good.
69. That's just 13.
What do you think there, Em?
I'm starting together.
Starting to
Yeah.
put itself together. It's all about like drawing the right picture, picking one equation that relates like the side lengths, basically, usually like whatever measurements they're giving you.
I just need to remember to get like the DL, DT on.
And so every variable is going to have that attached to it. Like when we were doing implicit a week ago, sometimes we had a dy dx, sometimes we didn't, right? Because we were doing ddx of x and y. Sometimes the variables matched, and sometimes it didn't. They'll never match in related rates because it's always ddt, right? We're always differentiating with respect to time, not length or width or height or radius or volume or anything.
Right.
It's always going to be with respect to a variable that is not in the problem.
Okay.
So every time you do the derivative, right, power rule or cosine, whatever, have that differential attached to it. Have a dl dt, a dh dt, a dr dt. Just put it at the end every step of the way. You'll always have at least 2 rates in there. You'll always have 2 of those ddt's because it's related rates. I gotta have 2 of them so I can relate them to each other. Next Friday, there'll be like, I don't know, I haven't written it yet, so we'll see, but volume of a sphere, Pythagorean theorem stuff, like nothing super crazy. And I'll give you whatever formulas you need. I won't make you memorize the difference between a volume of a cone and a volume of a sphere. I'll give those to you for sure. Because I know, at least for you, like in the moment during class, with enough practice, you're like, yeah, I get it. But then you come back and without being able to like peek back at your like the last thing you did, it's hard to remember. So, and I know how frustrating that's got to be for you because you're like, I knew this yesterday, right? I know. Listen, keep working hard and your grade will reflect it, I promise.
Thank you.
Because I know it's like,
I leave here feeling like
at this point, you're just like, you know, muttering words under your breath that I'm not going to repeat out loud. I'm sure I get that.
Right, but then I was gonna try to solve for DR.
Unless I want to start.
So I was gonna try to find the radius. I
You
don't
doing the
know.
spiritual movement?
Yeah, I think we need that one.
Spiritual movement.
Yeah, we got
I'm going to do 9 and 10 next page, unless anybody wants to see 8 any longer, the diagonal. Okay, again, the solutions will be up, so you can always peek back at them. 9 and 10 use that same rate up above, so draw the picture if you want. You don't have to.
Yeah.
Hi, Mrs. Rosen. I have a handful of yours, all hanging out.
No, this should be 4 or 5 times. What is that? 5?
Yeah, my project.
What number is that? So the DRP, that's one per second? 1 per minute? 1 per shoot, so we can,
Yeah, radius is.
Alex, what'd you pick?
I just.
What do you got?
Project. Pick the top.
Oh, yeah.
Camps in Colorado. Are there camps in Colorado?
Yeah, we have.
Okay. Timmy, what did you pick?
Huh?
What did you pick as your top one?
I'm doing all right. Oh, actual R square.
Oh, that's right.
All right, look at the notation they use, even imperial, right? Cubic feet written like that. So if you want to just be consistent, stick with that style. I'm cool with that. You'll probably see me do that the rest of the way.
And look, the 3 and the 4 are always canceled out.
40.
It's almost like they did it on purpose.
Right?
Like
The math.
whoever designed the volume of a sphere had it all figured out so we could do derivatives real nice. Cone too, right? 1/3 compared to amazing.
Per minute, right?
The only part about the cone is it's degree 3, it's 3-dimensional, but it's pi r squared h, so we never really get rid of the 1/3. This one's nice.
Oh, because it's already
Do some calculus there. What do you think? Of course it does. Math is science, and science is math. We just mostly focus on physics. All right, have a great day, everybody. I will see you mañana. Answers up by this afternoon, so you can start working on it. By the end of next week, have all these done for yourself. Happy to bye, Em. See y'all. Yeah. Which is great. No serious today. Yeah, you can tell by the thing that my background is good, so I can focus on it down. My mom does this stuff.
Yeah.
Alex could. Nancy could do it if you wanted to. Yeah. Probably the smartest kid.
I know. You're like 8? Yeah.
Yeah. They do that. Stop recording.
I've got you see.
Thanks. I'm ready for it. I am ready. Sam,